There is no specific National Electrical Code, or NEC, article that mandates concrete encasement for incoming secondary service conduits. The NEC provides minimum safety standards, but local jurisdictions and utility companies often have additional requirements. Several factors can lead to the requirement for concrete encasement even though it is not explicitly stated in the NEC. Firstly, physical protection is a primary reason. Conduits, especially those buried underground, are susceptible to damage from various sources including vehicular traffic, heavy equipment, and accidental excavation. Concrete encasement provides a robust physical barrier, safeguarding the conduits and the conductors within from mechanical stress and potential breaches. Secondly, the prevention of electrolysis is another significant consideration. Electrolysis occurs when dissimilar metals are in contact within a moist environment, leading to corrosion. While conduits are ideally made of compatible materials, variations in grounding systems and stray currents can still create conditions conducive to electrolysis. Concrete, being alkaline, can help to neutralize acidic soil conditions that promote corrosion and provide a degree of electrical isolation between the conduit and surrounding earth. Thirdly, fire resistance can also be a reason for concrete encasement. Although less common for underground service conduits, in certain applications where conduits pass through erroneous structures, fire resistance becomes a critical factor. Concrete provides a non-combustible barrier, delaying the spread of fire and protecting the integrity of the electrical system during a fire event. Local building codes often adopt or amend the NEC to address specific local conditions and safety concerns. These codes may mandate concrete encasement based on soil conditions, traffic volume, or other environmental factors. Utility companies also have their own standards and specifications for service connections. These standards are designed to ensure the reliability and safety of their electrical distribution systems, and they may include concrete encasement requirements for incoming service conduits. Determining whether concrete encasement is required involves several steps. Firstly, review local building codes and amendments to the NEC adopted by the local jurisdiction. These documents outline specific requirements for electrical installations, including conduit encasement. Secondly, consult with the local utility company to obtain their service connection specifications. These specifications detail the utility's requirements for incoming service conduits, including any concrete encasement mandates. Thirdly, communicate with local building code officials and electrical inspectors. They can provide clarification on local code requirements and interpretations, helping to ensure compliance. The NEC addresses conduit installation in several articles, although none specifically mandate concrete encasement for secondary service conduits. Article 300 covers general wiring methods and requirements for all wiring installations. Article 310 provides requirements for conductors for general wiring, including ampacity, insulation, and installation methods. Article 314 addresses outlet, device, pull, and junction boxes, conduit bodies, fittings, and handhole enclosures. Article 320 covers armored cable type AC, and Article 330 covers metal-clad cable type MC. Article 344 pertains to rigid metal conduit, or RMC, outlining its approved uses, installation requirements, and support methods. Article 352 covers rigid polyvinyl chloride conduit, or PVC, detailing its applications, installation practices, and support requirements. Article 356 addresses liquid-tight flexible non-metallic conduit, or LFNC, specifying its permitted uses, installation methods, and limitations. Article 358 covers electrical metallic tubing, or EM, describing its approved applications, installation guidelines, and support requirements. Article 362 pertains to electrical non-metallic tubing, or EN, outlining its permitted uses, installation methods, and support requirements. These articles provide guidance on selecting the appropriate type of conduit for the application, proper installation techniques, and protection requirements, but they do not mandate concrete encasement for secondary service conduits. The decision to require concrete encasement often stems from local amendments, utility company specifications, and site-specific conditions. Understanding the reasons behind the requirement and the relevant codes and standards is essential for ensuring compliance and a safe and reliable electrical installation. Concrete encasement provides benefits, but also adds to the cost and complexity of the installation. Therefore, it's important to understand the specific reasons for the requirement in a given location. The NEC does emphasize the importance of protecting wiring systems from physical damage, environmental factors, and other potential hazards. Section 300.4 covers protection against physical damage, requiring wiring methods to be protected from damage that could occur during or after installation. This section highlights the need to consider the environment in which the wiring system is installed and to provide appropriate protection. Section 300.5 addresses underground installations, specifying minimum burial depths for different wiring methods and voltage levels. While it doesn't mandate concrete encasement, it emphasizes the importance of burying wiring systems deep enough to protect them from physical damage. Section 300.7 covers raceways exposed to different temperatures, requiring raceways to be installed in a manner that prevents moisture from entering and accumulating within the raceway. This section highlights the need to consider the effects of temperature changes and moisture on wiring systems. Section 300.11 addresses securing and supporting wiring methods, requiring wiring methods to be securely fastened and supported to prevent them from sagging or becoming damaged. This section emphasizes the importance of proper installation techniques to ensure the long-term reliability of the wiring system. While these sections do not specifically require concrete encasement, they highlight the NEC emphasis on protecting wiring systems from physical damage, environmental factors, and other potential hazards. Concrete encasement can be one way to achieve this protection, but it is not the only way. Other methods, such as using rigid metal conduit, burying wiring systems deeper, or providing additional physical barriers, may also be acceptable. The choice of wiring method and protection method should be based on a careful assessment of the specific conditions at the installation site. When considering the impact of concrete on conduit systems, it's crucial to understand the chemical properties of concrete and its potential interaction with various conduit materials. Concrete is an alkaline material with a high pH level. This alkalinity can react with certain metals, leading to corrosion. For example, aluminum conduit can corrode when in direct contact with concrete, especially in moist environments. For this reason, it is important to select conduit materials that are compatible with concrete or to provide a barrier between the conduit and the concrete. Rigid metal conduit, or RMC, is a common choice for concrete encasement due to its inherent strength and resistance to corrosion. RMC is typically made of steel, which is protected from corrosion by a zinc coating. This coating provides a barrier between the steel and the concrete, preventing the alkaline environment from attacking the metal. PVC conduit is also commonly used for concrete encasement. PVC is a non-metallic material that is not affected by the alkalinity of concrete. However, PVC conduit is not as strong as RMC and may require additional support to prevent it from being crushed by the weight of the concrete. When installing conduits in concrete, it is important to ensure that the concrete is properly mixed and cured. Improperly mixed concrete can have a high water content, which can increase the risk of corrosion. Improperly cured concrete can also be weaker and more susceptible to cracking, which can damage the conduits. It is also important to provide adequate spacing between conduits and to avoid sharp bends in the conduits. Sharp bends can create stress points in the conduit, which can lead to cracking or failure. Adequate spacing between conduits allows the concrete to flow properly and to provide adequate support for the conduits. The NEC also addresses the use of expansion fittings in conduit systems. Expansion fittings are designed to accommodate thermal expansion and contraction of the conduit. This is important in concrete encased conduit systems, as the concrete can restrict the movement of the conduit and create stress points. Section 300.7b of the NEC requires expansion fittings to be installed where necessary to compensate for thermal expansion and contraction. The amount of expansion and contraction will depend on the length of the conduit run, the temperature range, and the coefficient of thermal expansion of the conduit material. Expansion fittings are typically installed at regular intervals along the conduit run. The spacing between expansion fittings will depend on the factors mentioned above. It is important to follow the manufacturer's instructions when installing expansion fittings. In addition to thermal expansion and contraction, concrete can also shrink as it cures. This shrinkage can also create stress points in the conduit system. To minimize the effects of concrete shrinkage, it is important to use a low shrinkage concrete mix. It is also important to cure the concrete properly. Proper curing helps to reduce the amount of shrinkage and to increase the strength of the concrete. In some cases, it may be necessary to use a special type of concrete that is designed to minimize shrinkage. These concretes typically contain additives that reduce the amount of water required for hydration. By understanding the properties of concrete and its potential interaction with conduit systems, it is possible to design and install concrete encased conduit systems that are safe, reliable, and long-lasting. Remember to always consult with local building codes, utility company specifications, and qualified professionals to ensure compliance and proper installation practices.